Dear students, here in this lecture we are going here first now we will go to the what is orbital quantum number. What is orbital quantum number? Okay, so the orbital quantum number basically represents the quantization of angular momentum. Quantization of angular momentum. So here I will tell you that how the orbital quantum number represents the quantization of angular momentum. For this, we will take our start with the differential equation. So we have the Schrödinger wave equation, and for the hydrogen atom, here we will take its radial part of equation. This is the Schrödinger wave equation for hydrogen atom. So here we can write it like this one. Schrödinger wave equation, radial part of Schrödinger wave equation for hydrogen atom is 1 over r square d by dr into r square dr over r into 2m divided by h square into e square over 4 pi epsilon naught r plus e minus L into L plus 1 over r square into r is equals to 0. Here you can see that this part totally depends on the r, so that's why this is the radial part of equation. This explains the radial aspects of electron motion, that is the motion towards or away from the nucleus. So here E here represents the total energy. E represents the total energy, which includes the kinetic energy of orbital motion, and also it contains about the radial motion. Okay, so the kinetic energy in here, there are the two kinetic energy, both due to the orbital motion of electron and due to the radial motion of electron around the nucleus. So here we can write the equation for the kinetic energy of electron. So the kinetic energy of electron can be written as kinetic energy due to radial part plus kinetic energy due to orbital motion of electron. Okay, so the radial kinetic energy of radial part, it represents the motion towards or away from the nucleus. Motion towards or away from nucleus. Okay, and now what about the radial part of kinetic energy, orbital part of kinetic energy? Orbital part of kinetic energy represents the motion around the nucleus. Around the nucleus. So these are the two contributions towards the kinetic energy of electron. Now we comes to the potential energy. What is the potential energy of electron? Potential energy and here of electron in atom. So it can be represented by the parameter u, and it is equals to minus e square over 4 pi epsilon naught r. So we can write the equation for total energy. Here the E total energy, which is the sum of kinetic energy due to orbital plus kinetic energy due to the radial motion plus potential energy. Okay, so we can put this value of energy into the equation of radial equation for the hydrogen atom. So our equation after putting this value will be, so we can write the equation after inserting the value of total energy E in radial equation for hydrogen atom. The equation will be equals to 1 over r square d over dr into r square d capital R over r dr plus 2m over h square into, here we will put the kinetic energy orbital plus kinetic energy due to radial minus, it will be equals to h square over 2m into L plus 1 over r square into r is equals to 0. So after putting the value of total energy, our equation will be like this one. Now we can separate here. We are going to discuss about the orbital quantum number. So our concern is about with the kinetic energy due to orbital motion. We have nothing to do the kinetic energy with the radial motion, so we will take only the kinetic energy due to orbital motion. So kinetic energy due to orbital, here according to this equation, will be equals to h square L2 L plus 1 divided by 2mr square. So here is the one two-step mathematics, and that will be that is very simple. I have written this value directly as the kinetic energy of orbital is equals to h square in L into L plus 1 over m2 mr square. So we also know that the equation for the kinetic energy is equals to, kinetic energy is always equals to 1 over 2 m v square orbital. Here as we are talking about the orbital kinetic energy, so this velocity will be due to orbital motion. And the total angular momentum, as we know that the total angular momentum is always equals to L is equals to mv r. Here the v is, again it is the orbital velocity, and L is equals to mv r. So here from this equation we can find out the value of here by squaring this equation. Okay, if we square this equation by squaring this equation, so our equation will become L square is equals to m square v orbital square r square. So here from here v square will be equals to L square over m square r square. So we can put this value of L square into the equation of kinetic energy orbital is equals to 1 by 2 mv square orbital So putting the value of v square here in this equation, we will get the kinetic energy orbital will be equals to L square over 2m r square. So this will be value, and here this one is the L, and the value of L is always equals to L is equals to L into L plus 1 under root, or and under root we know that this is the value of into h cut. So this equation represents the electron angular momentum. So this is the equation for electron angular momentum. So here, and L is the orbital quantum number. Okay, so as L is equals to L into L plus 1 underscore into h cut, and so L is the orbital quantum number, its value of 0, 1, 2 up to so on, so it can take these values up to so on. It is equals to n minus 1. So electron can have only a particular value of angular momentum L. So we can say that angular, like total energy, angular momentum L is both. It is the L is both conserved and it is quantized, as the electron can take only a particular value of L for the orbital quantum number. L is equals to 0, plus 1, plus 2, plus 1, so on. Okay, so here h cut, which is equals to h over 2 pi, and its value is 1.054 into 10 to the raised minus 34 joule second. So we can specify the different angular momentum states. Angular momentum states. So how we can specify the angular momentum states? For L is equals to 0, 1, 2, 3, 4, 5, 6 up to so on. So L is equals to 0 corresponds to the F state. This corresponds to the P, D, okay, F, G, H, I up to so on. There are the different, these states, angular momentum states, are called as subshells. So each subshell have its own quantized value of L, which corresponds to the total angular momentum. So angular momentum is quantized. So here we can write angular momentum for a different value of L for the different states, electronic states. So for the different atomic electron state, for n is equals to 1, n is equals to 2, 3, n is equals to 4, n is equals to 5, n is equals to 6. And so for n is equals to 1 corresponds to L is equals to 0, L is equals to 1, 2, L is equals to 3, L is equals to 4, and L is equals to 5. So for n is equals to 1, L is equals to 0. Here we have one S state. For n is equals to 2, we have L is equals to 0 and L is equals to 1. So for n is equals to 2, there are the different angular momentum states are 2s and 2p. For n is equals to 3, we have 3s, 3p, and 3d states. For n is equals to 4, we have 4s, 4p, and 4D states. In the same way, 5s, 5D. So here also I have the 4f state, 5s, 5p, 5d, 5f, and then there will be the 5G state. So here 6s, 6p, 6d, 6f, and 6G and 6I state. So for L is equals to 0, these all corresponds to the S states, to 1s, 2s, 3s, 4s, 5, 6s. For L is equal to 1, we have the P states. Either for N is equals to 2, it is 2P state. N is equal to 3, 3P, 4P, 6P corresponds to N is equal to 6. So in this way, we have different angular momentum states which corresponds to the different value of orbital quantum numbers. So thanks for watching. For more videos, please subscribe our channel.